Hello and welcome to another video. Today we are going to be talking about trigonometry 8 on projections. So topic 1 will be a quick review. In the last video we showed how we could think of functions as vectors. So let's say we have vector v. It has components 1 over 1, 1/2, and 1/3. We can think of this as f of n is equal to 1 over n, therefore making f1 1 over 1, f2 1/2, and f3 1/3. We can then take this and plot this as a graph of f1, f2, f3. Say this is 1, you would put it at 1, halfway point, and then about at the third mark, like so. And we can also use this as a graph, find areas under curves, which we will apply to integrals later in this video, or pretty much right now. Topic 2 will be on integrals as dot plots, or dot products, sorry. So we're going to take integrals a and b, and we're going to use these for the rest of the video. So integral a will be 1, 2, or have dimensions 1, 2, 3, where b will have dimensions 3, 2, 1. Now remember from the other video, yes, this is topic 2, but remember from the other video that you can find the vector norm of a vector by squaring all the components, and then squaring all the components, adding them together, and then square rooting them. So in the case of the vector norm of a1, that would be square root of 1 square plus 2 square plus 3 square, which comes out to the square root of 14. Now we can also establish this as something known as the dot product, where if we multiply two vectors together, their solution is their vector norms multiplied together times the cosine of theta. So, for example, in this case, we could say if vector A was multiplied by vector V and were equal to this, then that same result would be equal to 1 times 3 plus 2 times 2 plus 3 times 1. We can add this out to what we covered in our review, so we could write f of 1 times g of 1 plus f of 2 times g of 2 plus f of 3 times g of 3. We could rewrite this as a summation. Summation k equals 1 to 3, f of k times g of k. And this can be restructured into an integral that looks like this. The integral is 0 to 1, f of x times g of x dx. And we can use that as a basis for solving. Topic 3, we're going to be getting into some newer material. Topic 3 is going to be on scalar expansions. Topic 3 on scalar expansions and projections. So in our last video, we showed that vector A times vector B can be re-shown as something like this, where this would be A and this would be B. This angle here is theta. Now what we can do is we can increase size of these vectors by using scalar values. So that would mean if we had, say, 2 of vector B, that would be vector B, but twice as long. So let's say we're going to draw out a line here, or a vector here. Well, this will be our starting point. And let's say this vector from this point to here, this vector is vector 2b. Vector B would be at the halfway point, and let's say vector 1/2 would be right here. So it'll be 1/2 vector B. This can also go into the negatives. If we go the other way from our starting point, this would be represented as minus 1/2 of vector b. Now, as an important result, I would also like to note that if we take vector b and divide it by the vector norm of vector b, we get b hat, which will be relevant later on. Now, last topic, topic 4, we're going to be looking at projections using dot products. Push down a little bit. Topic 4, projections using dot products. So we noted that the vector norm of A we can rewrite as square root of 1 squared plus 2 squared plus 3 squared. We can expand this out and write it as the square root of 1 times 1 plus 2 times 2 plus 3 times 3, because that's basically what it is. And then we have 2 copies of vector A multiplied by each other. So basically, the vector norm of vector A is the same thing as vector A times vector A square root. So we can note that the vector norm of A squared is equal to vector A times vector A. Now we can look at projection as a vector. So if we take our image from earlier, and we'll have vector A and vector V, or vector B, I cannot talk, vector B, the projection of vector A and vector B is a line drawn at the right angle. It's perpendicular to vector B. And where that meets, that is where it is. So we can imagine, say, object emitting light up here, and it's emitting light down onto this line. And where the shadow is cast, that is our projection vector. So we can note that the projection vector of vector A and vector B is equal to the vector norm of A1 cosine of theta times vector B over the vector norm of vector B. We can combine these together to get the vector norm, vector norm of vector A, norm of vector B, cosine of theta, over norm of vector B, norm of vector B, times, all the way outside of the equation, times vector B. So this can essentially be thought as the projection vector can be thought as vector A times vector B over vector B times vector B, all times vector B. Bye, guys.